We're very happy to have Brennan from UCSD today telling us about the Callan Rubakov Effect.
Great. All right. Thank you very much to the organizers for inviting me. It's always fun to visit New York. And I think this is my first time visiting NYU, not for a conference. So it's really cool to just hang out and get the chance to talk to you guys. I'll be here through the end of the week, so I hope to have a lot of discussion. Right. So today I'm going to tell you about something called the Callan Rubakov Effect. And this is a problem that was realized in the late 70s, early 80s. It's about scattering massless fermions off of a monopole. So the sort of setting for our discussion is we have some, say, SU, so we're in 4 dimensions, first of all. And we have some sort of SU2 gauge theory. And if we add some sort of adjoint scalar field, then, and we introduce some potential for it, then if we choose the potential so that the adjoint scalar field condenses, then in the infrared we float to just, U1 Maxwell theory. And along this RG flow, there are some nice solutions to the gauge field called monopoles. So in the infrared, in the U1 Maxwell theory, as we all know, Dirac constructed some monopole solutions, which are just some sort of monopole line operator. And along this RG flow, they arise as some sort of smooth field configurations. And as we go to the infrared, they become the Dirac monopole. So what we want to do is we want to add some charged matter, so add some fermions in particular. And if we don't add any masses or Yukawa couplings, if we don't add any Yukawa couplings along this RG flow, they also flow to charged matter in the infrared. And so the problem of the Callan Rubakov effect, or rather the Callan Rubakov effect, occurs when you scatter these charged fermions off of the monopole. And what's interesting about this is that, so you should think of a monopole as some very dense object. So you can think of it as a really heavy ball, and there's just some magnetic field coming out of it. That's radial. But what's happening inside this ball is that you actually have, since you have a smooth field configuration, is you actually have the sort of UV gauge group restoration inside the core. And what's interesting about magnetic fields is that if you imagine, for example, you had a charged particle and you shot it straight at the monopole along a field line, since the Lorentz force is 0, it will just run into the core of the monopole and it will be able to detect the non-abelian gauge symmetry there. So this is some sort of classic example of some UV-IR mixing. Cool. So what's particularly interesting, and sort of the original setting for the Callan Rubakov effect, is if you imagine a standard model.
Why do you UV-IR mixing?
Because, so the direct monopole you define in the infrared by cutting out a hole and imposing boundary conditions there. And it's UV-IR mixing because the boundary conditions depend on the UV physics. Okay. And well, that's,
okay.
that's
fine.
the
Just want to understand.
Yeah.
So why is there no Lorentz force?
Just because it's V dot or V cross B. And if you're approaching along
Radially, yeah.
Yes. So good. So the original setting for the Callan Rubakov effect is you imagine the standard model is completed by some gut theory. And so it was fashionable back in the day to consider the SU5 gut theory that flows to the standard model SU3 times SU2 times U1. And what we're considering is monopoles along the hypercharge part of the gauge group. And then what you're doing is you're scattering standard model fermions off of this monopole in the hypercharge. And what was very cool about this is that Callan and Rubakov argued that if you scatter a proton, or in my convention I'll use antiproton, off of a monopole, you find that you get some anti-electron coming out. And so,
Answer the proton problem.
oh, thank you. Yeah, I think I have a, yeah, so you have an electron coming out. And so what's interesting is that, the point is that this gives you some baryon number violation. And so I think the original paper is called something about proton catalysis, or proton decay catalysis by monopoles. And so this is a very shocking thing that could happen in the universe. And I think actually this effect was one of the reasons that inflation was invented, was sort of to get rid of monopoles because they would sort of catalyze, well, not just because they catalyze proton decay, but this is sort of one major thing. So the Callan Rubakov problem is sort of has to do with this ... that I left unwritten. But something to note is that this extra stuff is sort of generally derived by physics, by symmetries. So this is almost completely constrained by symmetries. And in particular, if you take, if you imagine everything in the standard model is massless, there's no Yukawa couplings, and we're above the electroweak scale, then you're sort of forced to choose some ... dots that have a very strange interpretation. And in particular, these are what are called well, I guess what some people call fractional fermion states.
So that is kind of paradox arises already when the fermions are massive, like in the standard model context?
Yes.
Okay.
Yeah, yeah, good. So indeed, if you can also say this problem exists even with massive fermions, just by considering energy scattering that's sort of above, or sorry, parametrically below this the electroweak scale. No, sorry, below the gut scale, but parametrically above the mass scale of the standard model fermions, for example.
No, but if I really want to talk about standard model where all fermions are strictly massive,
Yes.
so is there?
That's actually what I'm going to talk about today. Is that most people don't use the mass, do the mass stuff because I think that it's an effective field theory argument is that this should just be a generic feature of scattering, because if you scatter at high enough energies, the mass is effectively negligible, and then you can treat everything as massless, and sort of all of the computations simplify.
Yeah, but this fractional thing business.
Yes,
still...
it's great. Yeah, so this is essentially what the whole talk is about. Is what do I mean by fractional fermion states, and well, yeah. So you'll see.
So
but,
another question.
Yeah.
Is this process unique to SU5 or is it very generic?
This is totally generic. It's sort of any time you have a U1 factor that comes from some UV gauge group, which I think has a fundamental, which is simply connected, say that. And then you can sort of modify it by saying, it's not simply connected, then there's certain monopoles that are smooth, and so. But yeah, generically, if you have a U1 factor in the infrared, this is what happens.
And you also have that, I say when it breaks down to standard gauge group, then you'll have this proton catalysis.
Yeah, right. So gut theories kind of have a, well, okay. Most gut theories, you can sort of have some breaking pattern that goes through an SU5 phase, or you can sort of connect it by picking some like appropriate scalar matter. I think one of the examples, okay. So yes, this is sort of a generic feature. Yeah. I can tell you more about like different gut theories later if you'd like. Right. So sort of the open problem, exactly what Sergey was talking about, is sort of what are fractional fermion states? And there's sort of been three sort of general attempts to explain this original analysis by Callan Rubakov. The first was given by Callan, is that you should think of this as some sort of density matrix. But that's actually not good because this solution actually leads to cases where you only have gauge charge conserved up to classical probability. And that's bad. The other sort of large class of solutions is that, or proposals, that there are extra non-perturbative sectors of the Hilbert space that you cannot access through the sort of normal semi-classical quantization of your gauge theory. But this has sort of a very conceptual issue. So, in the standard model, where this analysis was originally done, you have some sort of confining gauge group, and so maybe there's some weird issue with that. But you can sort of strip down all of the essential features to just this exact model. And because you're Higgsing the gauge group rather than letting it confine, you can pick this scale to be parametrically bigger than the confinement scale. And you can pick, the UV gauge coupling to be sufficiently weak so that this is a totally well-controlled RG flow where you're in a semi-classical regime for the entire thing. So this sort of goes against the sort of notion that there should be these extra non-perturbative sectors. And another reason why this is maybe a weird way out is that the energy density in the magnetic field falls off like 1 over r to the 4th in a monopole. So because of that, you can sort of really truly treat your asymptotic scattering states by just sort of the normal free field quantization. And this is at least what we'd expect. So there's a lot of sort of conceptual issues with this one. It's sort of just saying like, everything we said was fine because symmetries are nice, but it sort of didn't really resolve some of these conceptual issues. And the third class of solutions is that there are some additional interactions that we sort of miss. Until recently, there were sort of no suggested interactions. It was just sort of some idea that you can. A lot of the analysis is using rotational symmetry. Rotational symmetry. And so essentially, the point is that the analysis that was originally done is sort of only imposing rotational symmetry at the single particle level. But in general, since you have multi-particle states, or I guess multi-fractional fermion states, you might say that, well, maybe actually what's going on is that there's you're restricting to the j equals 0 component of some tensor product state. So this is sort of the status as of last August.
Sorry, but also Herman, I think that maybe there are some dionic states, so monopoles as a result of this process get excited.
Yeah.
So in what category
Good.
it belongs to?
So all of the analysis is assuming that there's some well, okay, that's not true. A lot of the analysis is done by actually just taking this picture and saying that, or just taking the infrared observer and saying like what could possibly happen. But even at the infrared level, the definition of the monopole actually requires you to have this sort of dionic phase. Essentially because the boundary conditions you're imposing here are that the magnetic field is coming out of it, but since the electric field and the magnetic field are non-commuting operators in your theory, you actually can't fix the electric field. And so necessarily you need some sort of Goldstone mode on the boundary, which we interpret as this dionic degree of freedom. But usually,
so that would be in what category in your?
Right. So this is jumping very far ahead, but essentially the point is that the dionic mode has a mass. So usually what we restrict to a monopole is we give this a very large large mass on the order of the UV cutoff. And so essentially the point is that you can't really use this as some sort of way to recover, to solve this problem, because it sort of doesn't exist in your effective theory.
Well, but maybe that problem indicates that there should be like that this expectation of that gap being large is actually wrong in the consistent UV series.
Yeah, okay. So that's essentially what my proposal is. So I'm going to propose something here. And it's roughly going to be what you said,
Okay.
but with some extra details.
The other works that talks about this scattering utilities sector will be within the second category among the resolutions.
Sorry, which
So the work from like David Toll and Komkowski and others.
Yeah, exactly. So, good. So, yeah, so the plan of my talk, the simple answer is yes. And the plan of my talk is, so I'm going to actually review how we arrive at these fractional fermion states. And then if you ask me, then I can tell you, sort of explain much more in detail what they're proposing. But I do want to emphasize that I'm sort of taking a top-down approach, so I'm taking some specific UV model and going to the infrared, whereas many people in this collaboration included sort of just start in the infrared and try to imagine all possible UV conclusions. Good. Yeah, so this is sort of the plan, and I also want to emphasize that I'm going to focus on the case where there are massive fermions. And there's a couple of good reasons to do that. One, as Sergey pointed out, is that the standard model has massive fermions, so this is sort of good for phenomenology. But sort of the more important technical reason is that giving the fermions a mass actually provides a nice sort of IR cutoff, well, IR regulator, if you wish. My understanding is that actually massless QED might actually not be a well-defined theory, but so this is a nice way to sidestep that. Okay. So let's first sort of go through what the original analysis of the Callan Rubakov effect was. So good. So we're going to stick exactly to this model. We're going to take some SU2 gauge theory, and I'm going to add my adjoint scalar field, and then I'm also going to add 2 times NF vial fermions in the fundamental representation. And I'm only going to include the gauge interactions and a potential for phi.
But kind of when you say that you consider massive fermions, you have in mind that there is some small U cover, or?
Good. So I will. So later, after sort of I show you what is weird about the original analysis, I'm going to sort of add a mass, and it's going to just be a small bare mass. If you add a Yukawa coupling, I think actually there'll be some very important phenomenological differences, just because if you have a Yukawa coupling that gives the fermions a mass, essentially the point is that the profile of the Higgs field goes to 0 in the monopole core. And what that means is that you actually have fermion bound states. And that's also that almost certainly has another effect when you consider the scattering and then trying to resolve gauge symmetry, gauge charge.
But your fermions are not chiral, right? So you're saying you can just add.
Yeah, exactly. Okay. So good. So I'm going to consider some RG flow where the scalar field condenses and a flow to U1 Maxwell theory plus 2 NF positive charge fermions and 2 NF negative charge fermions. And so the effective, the cutoff, UV cutoff of this effective low energy effective theory is going to be given by the mass of the W boson, which is the gauge coupling, UV gauge coupling times the Higgs field. And so, as I was saying on the first board, this RG flow has a set of smooth monopoles that flow to the monopole lines, the singular monopole lines in the infrared. And so what I want to do is I actually want to take the exact solutions and sort of do perturbative physics around them. So what I want to do is I want to consider only spherically symmetric monopoles, and that's really nice. Well, it's just a very nice simplifying assumption. And I also want to consider BPS monopoles. And the BPS condition is actually sort of unnecessary. The only reason why I'm doing this is because we know exact solutions. And they sort of expect that taking the BPS limit, which is essentially we imagine we take the limit where the Higgs potential vanishes. Essentially the only change in physics should be that this squeezes the core of the monopole. So it's sort of expected to lead to subleading effects. Yeah. Good. So with these two conditions, it actually turns out there's sort of a unique spherically symmetric monopole. And it turns out to be the sort of minimal BPS monopole. So by minimal, I mean the minimal magnetic charge. And so I can write out explicitly what this is. So if I pick generators Ti of my gauge group, then you can write it as Dirac monopole sort of embedded along the diagonal. And then you have some off-diagonal components. Here there's this profile function M, and the Higgs field also is embedded along the diagonal. And so what I've drawn here is actually this function h of r, and this function M sort of is complementary to it. This is the function M of r. And so this function M of r falls off exponentially fast with the mass of the W boson. So really what you think of is that this off-diagonal degree of freedom, this off-diagonal degree of freedom is like the profile of the charged W boson. Yes?
In the BPS limit, you have a massless Higgs, right? Or shouldn't the cutoff be lowered in that case? Why is the W mass and not the Higgs mass?
Sorry. You're saying that in this limit, that you're expecting that the EV cutoff should actually be the mass of the Higgs field.
Yeah, lambda V.
Yeah. I think that might technically be correct. But I think I think actually this but I think the scale that's relevant for this problem is actually still given by the W boson mass. I think that this is sort of independent. This field configuration is independent of the. Okay, so there's still a characteristic size here, and it's not given by the mass of the monopole. It's given by the W boson mass, which is kind of interesting. But
So you're gonna have a massless building the infrared standard test fermions. Massless scale.
well, the off-diagonal degrees of freedom of the scalar field are just eaten by the Higgs field, or eaten by the gauge field. The off-diagonal component
Right,
is
but
Higgs.
there's a Higgs factor.
That's right. So there's also the diagonal component. So indeed, there should be some sort of diagonal component here. That's massless, but it also is totally decoupled. It's charge neutral. Right. So in this limit where you take the Higgs value to be very large, this part, since this off-diagonal component, since it falls off exponentially fast, goes to 0, and the profile of the Higgs field gets squeezed so much that it effectively becomes a constant. And so now we want to do perturbation around this background. And so the perturbative degrees of freedom are this decoupled scalar field. Just there's also the photon, which is the diagonal component. So it's like this field A hat. And then actually there's an additional degree of freedom that we alluded to earlier called the dionic degree of freedom. And I'm going to call it phi hat. And one way to see that this there has to be this degree of freedom is that actually this this form of the gauge field is not gauge invariant under the infrared the infrared gauge group gauge transformations. Essentially, the point is that this off-diagonal component T plus minus does not commute with the generator T3 of the infrared gauge group. And so in order to make this actually gauge invariant, we have to introduce some sort of field that transforms like a Goldstone. And that's this field phi. And we're going to call it a dionic degree of freedom for the reason we'll see in a second. So if you put this phi hat into the gauge field, and then you plug it into the four-dimensional action, what you find is actually a one-dimensional quantum mechanics for this phi degree of freedom. It just looks like a charged particle on a ring. Oops. With a radius that's given by 1 over the W boson mass. And so phi is in this convention is 2 pi periodic, and we know how to quantize this theory in a Hamiltonian, which just looks like charged particle on a ring. And the Hilbert space is given by the momentum eigenstates. And so something that's important to point out about this Hamiltonian is that this is, sorry, clearly this first term is the kinetic energy. And the second term, since, okay, I didn't actually say this, A0 is the restriction of the bulk gauge field to the world volume of the monopole. And so what this term, the second term here, is actually saying that the it's a bulk coupling term. What it says is that the end state sources a bulk electric charge, which is 2 times n. Which is maybe not too surprising, because what's happening is this is literally the phase mode, charge phase mode of the W boson, which has charge 2. And so if you look at the state where it's spinning in time with a multiplicity n, then it's going to source bulk electric charge n. And so as Sophia was mentioning, or foreseeing, the Callan Rubakov effect is going to be the interaction of sort of bulk fermions with this ionic degree of freedom phi. Okay. So now I want to couple two fermions. And so again, we're sort of working in a totally semi-classical regime. So what we can do is we can just expand the fermions, do the mode expansion of the fermions in this fixed background. And because everything is spherically symmetric, this implies that you can decompose into angular momentum representations. And since everything is spherically symmetric, we can actually just, to simplify analysis, restrict the J equals 0 sector. So this is just the S wave scattering of fermions off of a spherically symmetric monopole. And this is consistent to leading order just because everything is spherically symmetric, including the dionic freedom. Okay. So now I can show you how the IR mode expansion works for the J equals 0 states. It's incredibly simple, which is nice. So the UV fermions in the SU2 representation sort of split up into these positive and negatively charged fermions. And because of this, your SU2-NF global symmetry is enhanced to an SU2-NF squared. So now if you can explicitly compute the mode expansion, and you find that these psi plus A are given by these effective two-dimensional fermions, or here this is some sort of constant spinner. And similarly for the psi minus, you have the exact same sort of mode decomposition, except that the positively charged fermions are ingoing and the negatively charged fermions are outgoing. So this is T plus R and T minus R. And also importantly, the constant spinner is polarized with respect to the radial direction. And the way you can sort of think of this is you think about some two-sphere that's surrounding the monopole. The J equals 0, the fact that these are polarized according to their electric charge is kind of like restricting to the lowest Landau level on each concentric two-sphere, and they happen to be ingoing or outgoing depending on their electric charge.
So here the monopole is in dot scale mass.
That's correct, yes. Yeah, the mass of the monopole goes like V divided by G. Okay. So now we have an effective two-dimensional theory. So we can imagine taking our spacetime to be look like this. So since R is only is the radial direction, it is only you're sort of on a two-dimensional half space, and so a scattering of some charged fermion is necessarily some chi, which has electric charge +1, and you have to have chi tildes outgoing to have negative charge. And so this is a totally non-unitary system unless you impose boundary conditions at R equals 0. And there's sort of two possible choices, or types of choices you could pick. You could say chi is related to chi tilde. Sorry, chi tilde dagger. With multiplication by some matrix for the flavor symmetry. Or you can have chi related to chi tilde by insertions of the dion. And as it turns out, you can just derive from the mode expansion and our background gauge field that this is actually the correct boundary condition, which is nice. And so what this would say is that if you scatter some ingoing chi mode into an outgoing chi tilde mode, you conserve gauge symmetry by depositing it into the dionic freedom. But there's a problem with this. And the problem is that the mass, essentially what that means is if you start from the 0 state of this quantum mechanics, you have to excite to the 1 state. And just by looking at this Hamiltonian, you can see the energy of the 0 state is 0, whereas the energy of the 1 state is m sort of order of the W boson mass. And so indeed there is actually a parametric scale separation set by your UV cutoff.
It's a good idea to use the moment basis for this diode at this point. I mean, so we know eventually the diode cannot stay, you cannot have a localized degree of freedom on the monopole all the way to the infrared.
Right.
So the, I mean, you would create, and you would at some point you want to create more like an harmonic oscillator than a
Yes, that's correct.
so, then why is it a good idea to think in terms of that basis? Or at which scale is it a good idea to think in terms of that representation of diode compared to the empty scale?
Good. So the reason why, the reason why people thought about this is they want to think about, or is that at least Callan and Rubakov were thinking about this as a virtual excitation. And so just because the ionic degree of freedom couples to all the fields, the idea is that you can virtually excite it, but then it immediately just decays back into the bulk fields.
Right.
Yeah. So
then why are we, it's like we are keeping an object of mass m W integrated all
that's right.
objects of mass
That's
m
right.
W.
So yeah, that's good. Right, exactly. So sort of from a top-down perspective, I'm about to integrate it out.
Okay.
But also from
Low energy perspective.
also from yes, yeah, also from the low energy perspective. Except there will be a slight catch that I'm avoiding at the moment.
But, so it's like but then the only possibility once you integrate out is a boundary condition of the kind you wrote above.
That's right. Right, yeah, good. So yeah, this is like maybe I should say UV boundary condition. Good. So, right, so to integrate, now we're going to integrate out. And so one nice way to integrate out phi, So the idea is that, as we said, phi hat is going to sort of decay to some sort of, outgoing modes, something like this. And one way we can sort of constrain what this is just by trying to construct the boundary condition that preserves all of the correct symmetries, all of the symmetries that you have in the UV theory, that the monopole actually reflected. And so the way that this is classically done is by bosonizing the 2D fermions. And so what that means is that I'm going to introduce some scalar fields, H, for the chi's, and some H tilde fields for the chi tildes. And this is just the two-dimensional number current for the chi and the chi tilde fields. And so what we want to do is we want to construct some sort of boundary condition where these j's are related by some matrix, these j tildes. And actually, because we're restricting to r equals 0, you can actually peel off these derivatives and just write the boundary condition in terms of these h and h tildes. And this matrix RAB is known. And this was actually derived by Callan Rubakov, although it was not necessarily formulated in this way exactly. The matrix. But this matrix RAB is the identity matrix, which from UV boundary condition is saying that chi reflects off the boundary into chi tilde. And then there is an additional term, which is the fully populated matrix, which is 1 over NF. So for example, for NF equals 2, we have a 4x4 matrix, which is like this. And so the physical way to interpret the, so this is like the sort of tree level scattering term, and this encodes this sort of decay mechanism. But now I can, and essentially the point is that the fact that this matrix is fractional is why people say that there's some sort of fractional fermion state going on. So, good. So in terms of the H fields, the boundary condition is H goes to H tilde A minus 1 over NF times the sum of all of the tilde A's outgoing. But if you fermionize this, go back to our original UV variables, or I guess our variables, what you find is that chi is related to chi tilde A times the product all of the chi tilde A bar to the 1 over NF root, or to the NF root. And so this is sort of where all of the confusion comes from, is that you're sort of creating a state with an operator that does not exist in your theory. And so this is the sense in which you have some sort of fractional fermion state coming out from the scattering process. And this is, I mean, as I presented it, this is a very ugly thing to see. But what's nice is that this sort of preserves all symmetries in our theory by construction. So it's sort of, it is nice if you think about it in the bosonic case. You say, well, 1 over NF, that's fine. But once you go to the fermionic case, it starts to become very weird. And so, so recently there was some work by David Tong and collaborators. And essentially what they did is they realized that this is not an allowed operation. Whenever you take the nth root of some operators in your theory, you generically introduce branch cuts into your correlation function. And so essentially the way you're allowed to take nth roots of operators is if you actually introduce some Z NF gauge field under which this operator has charge 1, and effectively what that's doing is it's reminding you that you're not allowed to take the nth root of your operator. And what it does is it sort of leads to this interpretation where you have some incoming fermion that comes out, and it's connected by this ZNF Wilson line. And since it's because it's a discrete gauge field, this is some sort of topological line operator. And so this is a very nice interpretation of this work. And also another way to think about this Wilson line is some sort of choice of branch cut in your theory. Well, at least in this state. So this is very nice. This is sort of what you can get in the infrared if you sort of just follow your nose. But the analysis we're doing today is actually taking some very, smooth gauge theory with some nice UV completion, asymptotically free. It has all of the nice things you could ever want. And so if you try to take this analysis and you uplift it to 4 dimensions, you get something that's a little confusing. So this branch cut becomes a branch, well, it's like a domain wall. It's at some sort of 3D branch cut in your 4-dimensional correlation functions. And so this is a bit confusing. And I think because we have everything is smooth and well controlled in this UV gut model, I don't think that this is what happens in that case. Although this could be that this happens in other UV completions of the monopole.
Sorry, and the small fermion mask, how does it affect all this?
this story.
Good. So great. So that's what I want to do now. Is to go into that.
Okay, so what's the mistake then? So like so far all you've said follows from, I mean branch cut is not a choice once you just follows from what you've done, right? So
Oh, like whether or not you introduce this branch cut, you mean?
right, I mean if that boundary condition attaches should reflect to some weird vertex operator, right? So,
That's right, yeah.
so where is the mistake if this is not the right answer?
Very good. So we'll do that now.
But there is a mistake. That's so far. That's
Yeah. And I think it sort of all comes down, well, okay. It's a really hard mistake to see in the massless limit. This is something I'm sort of planning on investigating, but we'll comment more on the massless case a bit. So I want to go back to this quantum mechanics. Quantum mechanics is nice. So this quantum mechanics has a topological term you can add to it. Which is just like a theta term. And what happens when you add this is that your momentum operator sort of shifts by a constant. That's dependent on this theta. And it also shifts to Hamiltonian here. So your Hamiltonian is this squared. Then you get a minus theta over 2 pi. And this is sort of the effect of shifting this term. It shifts the Hamiltonian, it shifts the momentum, but it doesn't shift the Hilbert space. But what it does do, or something else it does, is it shifts what the sort of ground state is. So, so now the ground state is theta dependent. And so if you, for example, if you start in sort of the 0 state with theta equals 0, if you shift theta, it goes to theta plus 2 pi, you find that the ground state is then going to be given by the 1 state. And so because of this fact that the quantum mechanics sources a bulk electric charge, what this shows is that you go from some sort of monopole, which has a bulk electric charge 0, to a monopole, which has bulk electric charge 2. And this should be familiar to us from sort of four-dimensional physics. And in fact, this is actually just coming from some four-dimensional theta term. This is literally just the Witten effect in the quantum mechanics. If you take the term theta and wedge and you integrate along the two-sphere that's linking the monopole, you find that this becomes theta 2 pi and the time and then the electric field in the radial direction. And then since this is a total derivative, you can bring it to a term on the monopole world volume, and you find that this is just theta over 4 pi naught minus 2a dt, which is exactly the term I wrote down. Up to a factor of 2, but this is exactly what we would want. And so one place this you can get theta terms is you have massive fermions with some sort of mass which is complex. This leads to some theta angle which is given by alpha, well, proportional to alpha up to some number that's dependent on the representation. And so this Witten effect you could think of as by actually taking the fermion with complex mass and quantizing it and figuring out what the vacuum state is in the monopole background. And what you find is that there's actually an electric charge density in the vacuum. It has some exponential fall off in the mass of the fermion with a total charge which is proportional to theta. So that the Witten effect, you can actually see it by looking at the fermion vacuum. And so my claim is that the Callan Rubakov effect is actually resolved in this setting by a dynamical shift in the theta term. I swear I didn't write that. Very clever. Okay. So I know I'm running low on time, and I always take way too long on background, but I'd like to motivate for you sort of how this happens. So I've sort of stayed away from writing down any sort of action or Hamiltonian or anything for this two-dimensional theory, but you can actually derive it completely by taking this mode expansion and just plugging it into the action, and then just integrating appropriately because you have mode functions. You have everything you need to do this computation. And so if you compute what the two-dimensional theory is, then you're going to find the following. So first I'm going to introduce fermions, all with a bare mass m psi. And I think I erased everything, so I'm going to take it so that the theory has some symmetry, which is an SUNF. Good. And so now I'm going to use some bosonic variables to write the action because it's easier. So I'm going to use some index lowercase a, 1 to nf. Right. So I'm going to introduce bosonic variables, which are these original HAs plus H tilde A's. And for short, I'm going to write H without an index as the sum of all of these H's. So something that's nice about this decomposition is that this is actually an uncharged complex scalar field. So it does couple to the gauge field though through its sort of, it couples to the gauge field as follows. So your action looks like dH squared. Now you have a mass term. And then it couples to the gauge field, F, T, R, and H. And you have a kinetic term for the gauge field. So this is the bulk action. And now you have the boundary term, which includes this ionic quantum mechanics. So since this field HA is uncharged, the gauge field actually couples to DH. And so when you integrate that by parts, you get a coupling that looks like this, that's gauge invariant, and you get a boundary term. And this boundary term acts exactly like a theta term in the quantum mechanics. And so now if you think about scattering, so these chi-fermions turn into H kinks. And similarly for chi-tildes. And so the idea is a scattering looks kind of like this. You have some incoming H kink, which reflects into some outgoing H tilde kink. And in total, what this looks like is some field H. It looks like some field H, which winds by 4 pi. And so what that means is that actually, when you do this scattering, you've done this displacement of the boundary H field by 4 pi, so that the ground state, the ground state shifts from 0 to the 1 state. And this is this is how essentially the gauge charge is conserved. So sort of
Sorry, I'm a bit lost. So this H field, it's gauge neutral, it's not.
yeah, that's right.
So the,
But you're still, this is just the presentation of the theory in this way. It's essentially, if you think about this picture in terms of the H kinks, so just, sorry. So we know from the bosonization map that this chi is like e to the I of H. And so the H kink is really a phase rotation of this chi field. But we also know that chi is the phase of the four-dimensional field. So really the picture is that when you do this scattering, the phase of your four-dimensional field is actually spinning. And because there's a mass term, you can think of that as it's really like an axionic phase rotation. And so what's happening is you have this big, I guess, spherical shell coming in where the phase, essentially the vacuum structure is changing. And it comes in and out in a way that, so that the sort of bulk 4D theta term changes by 2 pi, 4 pi. And this causes the shift in the vacuum. So that it actually carries the electric charge that you are depositing when you look at this tree level scattering process. And so, sort of the proposal that I have is that scattering of a four-dimensional fermion of a monopole in a gut theory occurs as if it was a tree-level interaction with a W boson that's trapped in a monopole core, where you sort of dynamically shifted the theta angle. And so this is kind of like a dion. But it's very important to point out that this is not a Julia Z dion because of this parametric separation of energy scales. You're not putting in enough energy to bridge the gap. In fact, if you look at, so I told you that the size of this charge cloud is set by the fermion mass. So what that means is that the amount of energy you need to put into the electric, in the vacuum state is actually also parametrically scaled like MSI. So you're allowed to do this as long as you have enough energy to actually send in a fermion. But now you could ask about the, oh, sorry.
Yeah, where in this two-dimensional theory did you input the fact that we had this charge density in the vacuum?
Good. So I actually have not fully solved this two-dimensional theory. It was more like you realize that this has a four-dimensional avatar, and this sort of shifts the vacuum of the quantum mechanics. So the quantum mechanics, it doesn't see this energy. It's actually going to be in the bulk electric field. So essentially what you need to do is you need to realize that there's a back reaction because of this coupling to the bulk through A. Yeah, so that's how you should be able to see that there's this energy and how there's a bulk electric field. So indeed, if you integrate out this quantum mechanical degree of freedom, you'll find essentially a shift in F here that'll source H, which will fall off Well, should have sorry. Yeah, you should just find a shift in F, and then this part here will contain all the energy.
Your sense of the consciousness and you're going, distance is much larger than the quantum wavelength of the fermions. There you said that you see something like object which has a certain charge. Seems obvious from multiple expansion.
Yeah.
Like like I mean like I should have been, is this just a statement or is there a more, I think you want to make a more intrinsic statement about this state.
Yeah, I think the point is that yeah, so I think the statement is that such a state exists. It was not obvious that that state should exist. That was the whole problem that we ran into. Was that we thought it took a parametrically large amount of energy to leave that electric charge behind when you do the scattering process. But what I'm telling you is that that's not true.
So basically you're saying, let's forget about scattering, you're just saying in the initial series there is a monopole state, but there is also this dionic state which has mass difference of the m psi.
Exactly. And essentially the point is that it's true that the theory, the infrared theory, the deep infrared theory has a symmetry, but you can say theta is identified with theta plus 2 pi. But that's only true if you do this redefinition of your line operators, because it shifts the electric field of the monopoles. So this sort of only appears like a true dion when you go to energy scales that are much lower than the fermion masses where you integrate them out. Then you can't tell the difference between a Julia Gies ion and this type of ion.
Because when the mass of the BPS dion is much bigger. Right?
Yes, that's true.
So this is not the BPS dion. That was supposed to be the lowest mass dion. So
that's right. But if you're at energy scales where this mass scale is infinity anyways, then you can't tell the difference. Or if it's above your UV cutoff, then you can't tell the difference.
Sorry, you're saying that.
well, I mean, for any given electric and magnetic charge, you can compute what is the minimum mass, right, in this, the BPS limit.
Yeah.
It is what it is, but it's much bigger than the mass of the
That's correct.
monopole. So here you have something. I don't know what is this state.
Yeah.
So what is?
Sorry.
So you're saying this state cannot exist.
Well, I mean,
No, it's just not the usual BPS dion state.
But I thought BPS bound applies to any state which has
Yeah.
certain charge, right? So how this state avoids then?
so
So the BPS bound assumes that there's a fermionic vacuum that's trivial. So it's saying that they're exciting the electric field by purely kicking the dion so that you're in the theta equals 0 vacuum and the momentum state 1 of the W boson.
So I'm saying that BPS bound here is not real, it's just a kind of technical property of the classical equation. It's not related to any actual supercharge, and so in that sense it's not.
Yeah. Right. So yeah, good. So you derive the BPS equations you derive by taking the bosonic Hamiltonian and saying F equals d phi. Well, it's one of them at least. There's a couple other. But it's by you do this sort of trick where you write the Hamiltonian as some sort of exact total sum of squares up to a total boundary derivative, and then you say, well, and then you just do some analysis there. But right, so that's for a totally bosonic vacuum with a trivial fermionic vacuum. This is saying that there's actually something sort of tricky that goes on when you consider non-trivial fermionic.
Can I supersymmetrize the full setup such that BPS bound becomes really the actual bound?
So if you supersymmetrize, then you have to introduce a Yukawa coupling.
Okay.
And then everything's totally different. Because then then you could potentially say that maybe this state is actually just a true fermion bound state.
So like if I were to, let's say, if I were to be at energies between MW and psi, then I should be able to integrate out that dion that you showed us before. So this is the state that they observe from this low energy theory, from this theory between MW and psi.
So you didn't actually need any of this analysis to arrive at this conclusion. It's sort of just, the idea was that I sort of wanted to show how there's this additional term that was missed and how it has a dramatic effect because of this interpretation of the bulk.
Sure, but I mean, what is this D? I mean, again, that's the question. Like, now I'm integrated out the diode, right?
Yeah.
So, what is D? This D.
Okay, so it's really this state. It's saying that the monopole vacuum with this monopole is the monopole state in this fermion vacuum, non-trivial fermion vacuum.
But I mean, it's an excitation of fermions, right? Again, like I'm just trying. So.
But it's not part of the EFT which was initially introduced, right? It's really, the statement is UV consistency requires.
Yes.
No,
Such
no,
additional-
like you can integrate out the time, like we do energy without it, there is no problem with that.
Yeah.
But now there is this state. And again, I think the analysis you showed before with the boundary condition there tells you how to write this state in some very unintuitive form. It's that state or not?
Right. So good. So this is sort of what I think is probably the next step in sort of understanding the Callan Rubakov effect. Is sort of understanding what the scattering with shift in theta means. I think this is going to be a memory effect. So it's I think you're asking all the right questions. I think it's I think it's non-trivial enough to totally appreciate. Yeah.
But is this something that you can hope to understand even in the massless limit? Or you have to consider small.
Good. So yeah. So if you take the massless limit, sort of it becomes a bit confusing because now the sort of charge plug goes off to infinity. It becomes infinitely dispersed, but it has a finite charge. And I think this is why this effect has sort of always been missed because people only take the massless limit, and you just sort of can't see this effect there.
But is it obviously contradict to this story to Zohar and David? Because their story, as I understand it, is really strictly in the massive limit, right? Massless limit.
Yeah.
So could it be that basically this massive story in the massless limit reduces to what they're saying?
It's absolutely possible.
Right. So it's, I don't see there's
No, I don't think there's a contradiction,
Right.
but I just don't understand what that mapping would be because of essentially because you have this like space filling branch cut. Maybe you should think of that as some sort of different phase.
Well, maybe that branch cut is kind of reflective of this.
Yeah,
It's a different user sector.
Yeah,
Right?
it's
Definitely
totally
charge product expanding it.
Yeah, no, it's totally possible. I definitely don't understand it. But also, if you do this scattering at energies much higher, or parametrically higher than the mass of the fermion, you would sort of expect to recover the same sort of physics that you would get in the massless limit. So that's sort of. So yeah, I think I don't know the full answer of what happened in the massless limit, but I think this is at least a step in the right direction. And okay, so I don't want to go on for too much longer, but I did want to make a couple comments. One is about the sort of Dion stability. Essentially, the point is that the fields in this theory and the infrared theory couple to bundles of this form. So this is sort of the symmetry structure, if you like, of all the infrared fields. And what this is telling you, this Zn quotient, is that all interactions that preserve gauge symmetry also will sort of preserve SUNF symmetry mod Zn. So essentially, I'd like to argue that, suggest that the Dion is actually stable mod NF. So the Dion, well, say the monopole in the NF state has the possibility to decay to the monopole state in the zero state plus a number of outgoing fermions. And in fact, because of this NF quotient, you get one fermion state in each outgoing mode. And this actually, as part of the proposal, actually matches the Callan Rubakov effect exactly. So the second comment I wanted to make is that this proposal matches the Callan Rubakov proposal or result essentially whenever the Callan Rubakov effect didn't have this fractional fermion issue. And I also wanted to comment this can actually be generalized to higher angular momentum modes, which I do in my paper. But anyways, I don't want to take up too much of your time, so I'm gonna stop there.
More questions? I still don't understand what is this fermion vacuum. Normally you would say fermion vacuum is a Fermi sea for some fermions or some other fermions that in some cases are related by Fourier transformations, or there are some condensates. So what is that?
Yeah, good.
Is there a condensate?
Yeah, I think that's probably the best way to think about it. And I think I had started to say that actually over here. So I was saying that if you can figure out this ionic mode with a non-zero theta angle, so you sort of restrict to the vacuum state, and you find that there will be some source here for the gauge field. So this part will just lead to this energy ordered m psi, like I was suggesting, but this term acts like a source for the bosonic field H. And so I think what that means is that actually there's going to be some sort of small, you can really think of this as some small cloud that's sort of bound to the or condensate rather, near the monopole.
So can I think about it as some maybe singular classical solution and fermion something like that? Because for smooth classical solutions there is BPS bound, right?
But it is important that it's the BPS solutions are all bosonic. This is not just bosonic, it's also fermionic.
Well, but normally I would think okay, you find classical solution and then okay, there are some polarization effects which you can study, but they won't change that dramatically the mass of the solution. Right? So that's
They wouldn't bring infinity to epsilon.
right.
Yeah.
So yeah, I'm trying to see what is there, how to think about it. Is it should I think about it as somehow I should include some singular classical solutions and
well, I mean, in the infrared, these solutions are technically singular because it's a monopole, it's a singular direct monopole field.
no, I'm
Okay.
asking from the UV theory.
From the UV theory.
Right, yeah.
I think the UV theory just knows about this intrinsically.
No, but basically the question is there a calculation one can do in the UV theory without, which doesn't start with monopole and scattering around monopole, but just directly looks for,
Just from
is there directly, is there a calculation which discovers this
Yeah,
state
couldn't you
exists?
do, say, include the fermion condensate by the Hilbert-Stratonowicz, by saying psi bar psi equals sigma, then you plop it into the you
Yeah,
find something, or you find some self-consistent action, some.
yeah, I think, yeah, so I think this might have actually been done. I know there's a lot of literature on computing the fermion condensate in the presence of the monopole. I think it is just maybe not interpreted in this way.
But I would think if you just really start with some classical monopole solution, or dion solution, and consider some fermionic effects like that, they will shift energy by amount of determined by MF, not by mGAT, right? So
Yeah.
Here the energy shifts dramatically.
But maybe you shift up from the monopole mass, not down from the dion.
Yeah, you should be shifting up from the monopole momentum.
I see.
Do you think this kind of solution has been studied?
Yes, I think so. There's very large literature. I feel like it's also very, yeah, I believe it has been, but it just was not maybe interpreted in this way. Yeah, I think sort of the key to making this sort of to coming into this sort of conclusion is that you do have to consider the mass of fermions. And the reason why maybe people didn't want to do this is because when you have massless fermions, you have exact chiral symmetry. And when you have the exact chiral symmetry, you're sort of forced to pick boundary conditions that are weird. You're sort of forced into the Callan Rubakov problem. When you have massive fermions, you're not actually forced into this. But dynamics gives it to you anyways.
So I can understand this as that model as sort of a UV completion, or partial UV completion of the story of Zohr and the others, the massless limit, just because you have this extra line and you're, rather than starting with a weird boundary condition, you're starting with the intuitive one and getting the same result.
That's totally possible. I don't understand the true relation of taking the massless limit to that. I can tell you more of my thoughts about the massless case. But I actually, I believe someone's doing a computer simulation of this right now. So we'll soon find out.
So the two-dimensional theory,
I think they're doing a four-dimensional simulation. I think it's Rubakov Effect.
Let's end the game.